Hey, good morning, class, and welcome to Lesson 5.1.2. The objective today is I will understand how horizontal shifts and vertical stretch transformations impact an exponential function. Now, let's just recall a couple of things. We're going to recall some information regarding a transformation and then some exponent properties. First of all, a horizontal shift. If you think back to the work that you've done with transformations, if we take a function f of x, and if it's equal to x squared, a parabola, if I shift that x plus 2 units, that's actually going to shift it 2 units left. So my new function would be moved 2 to the left. If we take f of x minus 3, this is actually going to shift our function 3 units to the right. 1, 2, 3, and that would be where our parabola vertex happens to be at 3, 0. Now for a vertical stretch. If we have 2 times f of x, that's going to give me 2 times x squared. This is going to make our graph twice as tall. So every output value becomes doubled, and our graph gets stretched upwards by a factor of 2. So it's 2 times taller. And if we were to take and graph 1/2 f of x, that would be 1/2 x squared, then our graph becomes half as tall, or it's multiplied vertically by a factor of 1/2. Now, reviewing some exponent properties. If you have x to the a times x to the b, that's the same as x to the a plus b. In other words, x squared times x to the 5th becomes x to the 7th. And if you have x to the a divided by x to the b, that's the same as x to the a minus b. Now sometimes you'll see it written like we have here on the left in the red rectangle. Other times you'll see x to the a over x to the b, and that would be x to the a minus b. Or if I had x to the 3rd over x squared, that becomes x to the 3 minus 2, or just x to the 1st power. And here's your power property of exponents. X to the a raised to the b is the same as x to the a times b. Or if I had x cubed raised to the 4th power, that's the same as x to the 3 times 12, 3 times 4, which is equal to x to the 12th. Let's take those skills and apply them to exponential functions. Can two different transformations give the same result? To explore this, consider the exponential function k equaling 5 times 2 raised to the 3 times x minus 2. Can this equation also be written in the form of a times b to the x? Work with your team to determine if it's possible to rewrite k of x using only a vertical stretch. If so, justify your decision. If not, explain completely why it does not work. So let's take some of those properties and apply them to this particular problem and see if we can't change k of x equaling 5 times 2 to the 3 times x minus 2 into an a times b to the x. Well, here's what I'm noticing first of all, is that we've got a little multiplication taking place here. We have 3 times x minus 2. That's an example of our power property. So let's rewrite this as 5 times 2 to the third power raised to the x minus 2. Well, 2 to the third is 8. So now I have 5 times 8 raised to the x minus 2. I have subtraction in my exponent. If you go back a slide, subtracting 2 terms in your exponent really becomes the same as taking 8 to the x over 8 squared. Now, 8 squared happens to be 64. So now I have 8 to the x over 64, which is equal to 5 times 1 over 64 times 8 to the x, which gives us k of x equaling 5 64ths times 8 to the power of x. Now, continuing to apply some of these skills, we applied some exponent skills on the previous slide so that we could rewrite an exponential function in terms of a times b to the x. Now let's apply some of the transformation skills that we reviewed at the beginning of this lesson. Working with exponential functions, it's not surprising that the properties of exponents are needed. Consider the function f of x equaling 3 to the x. Sketch a graph of y equaling f of x. I'm going to sketch this graph. I'm going to choose a few points, x, f of x, and one point that we definitely want to use is 0, 1, and 2. But let's also go with a negative 1. So 3 to the 0 power is going to be 1. 3 to the first power is 3. 3 squared is 9. And 3 to the negative 1, well, that's 1/3. So if I was to graph these points, negative 1, so 3 to the negative 1 is 1/3. That's way down here. I don't want to use the highlighter. I want to use the blue pen. That's way down here. And then 3 to the 0 power is 1. 3 to the first power is 3. And 3 squared is 9. So my graph looks something like this. Where's my exponential curve? And don't forget, there is a horizontal asymptote on the x-axis. In other words, as x goes to negative infinity, this function, f of x, is getting closer and closer to 0. Now, let's take a look at part B. Write an explicit equation for and sketch a graph of g of x equaling f of x plus 2. So I'm going to take my equation, let's go with a green pen. G of x is equal to 3, and I have to raise this to the x plus 2. Now when I'm adding exponents, that's really 3 to the x times 3 squared, which is equivalent to 3 squared is 9 times 3 to the x. Now that's the equation for g of x, but I can actually graph this by just applying a transformation. This is really moving f of x 2 units left. So I'm going to take all of my points in f of x and just move them 2 to the left. So that first point was a -1 up 1/3. So that's going to now be a -1 moved 2 to the left. That's going to be a -3, 1/3. I had a point of 0, 1. Move that 2 units to the left, 1, 2. So that's now a -2, 1. There was a point on f of x right there. That was 1 over and 3 up. Well, that has to be moved 2 to the left. So that's now going to be a -1 and 3 up. And then this point was 2, 9. It has to be moved 2 to the left. So that's now going to be 0, 9. So here's the graph for g of x. Now what I'd like you to do is pause this video, go to your calculator, and type in 2 different equations. Type in 3 raised to the x plus 2 as y1. See what that graph looks like. And then type in 9 times 3 to the x as y2. And take a look at that graph. I think you'll find that they are exactly the same, and they look just like the green graph up here for g of x. So take a minute, pause this, and graph those, and then come back. Okay, welcome back. Let's take a look at h of x. They want us to write the function for h of x. Now this is 9 times f of x. This is going to make it the graph 9 times taller. And so, choosing a different color, let's go black. H of x equals 9 times 3 to the x. We're going to take that table that we had over here for f of x and recreate it. So there's x, there's f of x. This was a -1, 0, 1, 2. My output was 1/3, 1, 3, 9. We're going to extend this for h of x. H of x is 9 times whatever f of x was. So 1/3 times 9 is 3. 1 times 9 is 9. 3 times 9, 27. 9 times 9 is 81. Now let's graph those points. Unfortunately, I can only graph the first two because of my coordinate plane up here only goes from a -10 to 10 for x and y. So let's graph these 2 points, -1, 3, and then 0, 9. And what I notice is I have the same graph as g of x. So my graph looks like that. with that horizontal asymptote on the x-axis. So what we've noticed is that the graph of g of x, the graph of h of x, they are the same because a horizontal shift of +2, that means 2 units to the left, is the same as a vertical stretch of 9 times f of x. In other words, if we make it 9 times taller. So let's take these properties that we had on the last couple slides and apply these. It says for us to let f of x equal 3 times 4 to the x. Use properties of exponents to show that each of the following equations is true. I'm going to do B, and then you can pause this. You can do part A, and then check your work. So f of x is 3 times 4 raised to the x minus 1. Does that equal 1/4 times 3 times 4 to the x? Well, working the left side, this is 3 times 4 to the x divided by 4 to the 1, which is 3 times 1/4 times 4 to the x, and 3 times 1/4 is 3/4 times 4 to the x. Now on the right side, I have 1/4 times 3 times 4 to the x. Well, that's all multiplication running through here, so I'm going to take 1/4 times 3, and that is 3/4 times 4 to the x, which we now have 3/4 times 4 to the x equaling 3/4 times 4 to the x. Pause this, and you try A, and then come back and check your work. Okay, welcome back. So f of x plus 2 equaling 16 times f of x. On the left side, that's going to be 3 times 4 to the x plus 2. On the right side, that's going to be 16 times 3 times 4 to the x. Simplifying the left side, 4 raised to the x plus 2 is 4 to the x times 4 squared. Well, 4 squared is 16. 4 to the x is just 4 to the x. And so I have 3 times 16, which is 48, times 4 to the x. On the right side, 16 times 3 times 4 to the x is the same as 16 times 3 times 4 to the x. It doesn't change, and 16 times 3 is 48 times 4 to the x. So f of x plus 2 does equal 16 f of x. If you'd like, you can just pause this and read through 515. Part A, where you're comparing the graph of 2 to the x plus 3 to 8 times 2 to the x. And it's showing you how a horizontal shift of 3 units to the left would be the same as a vertical stretch of 8 times your function. So just read through it, take a look, see what you see for some similarities, differences, and how it all compares to y equaling 2 to the x. Hopefully, what you're noticing is that 2 to the x plus 3 is the same as 2 to the x times 2 cubed. 2 cubed is 8, so I have 2 to the x times 8 which then is the same as 8 times 2 to the x. So that horizontal shift left is the same as that vertical stretch by a factor of 8. Now, what we need to do is try to prove that this happens to be true. Graphs help us show that something is true, but we still really should try to prove it. So graphs help demonstrate why, but they do not prove that for any exponential function, every horizontal shift is equivalent to a vertical stretch. Algebraically prove that the two forms y equaling b to the x plus h and y equaling a times b to the x are equivalent. That is, a horizontal shift is equivalent to a vertical stretch. So I'm going to prove that b to the x plus h is the same as a times b to the x. Now we're noting that a, b, and h are all real numbers. So b to the x plus a horizontal shift of h units, that's the same as b to the x times b to the h. So I'm going to rewrite that as b to the h times b to the x. Now b is a real number raised to a real number. That's going to give you some real number. Let's call b to the h, that real number, let's call it a. Therefore, I have a times b to the x. And that's what I wanted to come up with, a times b to the x. If you want to take a look at the next slide, feel free. In your learning log, describe when and how a horizontal shift is equivalent to a vertical stretch, then show steps needed to rewrite a times b to the m times x to the h plus k in an equivalent form and make up your own example. Title this Equivalent Forms of Exponential Functions. If you want to pause this and try to simplify this or write it in an equivalent form, please do so, and then you can come back and check your work. All right, welcome back, and here is the quick wrap-up of the lesson. We're going to take y equaling a times b raised to the m times x minus h plus k, and really try to rewrite this in the form of y equaling a times b to the x plus k. Starting out, there's your statement. You have a property of exponents that says m times x minus h, your power property that is the same as b to the m raised to the x minus h. Now, b to the m, if you take b as a real number and you raise it to a real number, you're going to get a real number. Let's just change the name of it. Instead of having this statement of b to the m, let's just call it b sub 1. So I'm going to replace b to the m with b sub 1. So my statement is now a times b sub 1 raised to the x minus h. Well, using that property of b being raised to subtraction in my exponent, that is really b sub 1 to the x divided by b sub 1 to the h, and then I got my plus k. That is equal to a times 1 over b sub 1 to the h times b sub 1 raised to the power of x plus that constant k. Simplify this expression, I get a over b sub 1 raised to the h. That's supposed to look more like an h there. Times b sub 1 to the x plus my constant. But we know that if you take a real number a and you divide it by a real number raised to a real number, you're going to get a real number. Let's call that real number a sub 1. So now I have a sub 1 times b sub 1 raised to the x plus k, which is exactly what we were trying to do. That's an equivalent form. Any of these throughout here is basically an equivalent form of our original statement. Hopefully you enjoyed this video. Please take advantage of the office hours, take advantage of the exit slips, take advantage of the supplementary videos so that you can develop the skills necessary to be successful in the pre-calc class. Enjoy the rest of your day and look for lesson 5.1.3 in another day.